Hello everybody. This lesson is going to be some examples of stoichiometry problems that are a little bit more related to a real life story. And one of the things you need to make sure of is that when you get one of these real life stoichiometry examples, that you answer the question that's actually being asked. So often people will get a final numerical answer, but they won't actually answer the question that was asked. So that's what we're going to practice today. When you do your KCQ boxes, there's not going to be much to put compared to normal, but the big takeaway that you should make sure you're reflecting on is the idea that when there is a story present in the problem, you can't forget about that part too. Okay? All right. So the first story, the first example is going to be about airbags. So the exact quantity of nitrogen gas must be produced in an instant. So there's a chemical reaction that takes place inside the airbag, and it fills with nitrogen gas, and that's what inflates the airbag. So it's really important that your airbag inflates the right amount. If it's too little, that's not safe. If it's too much, that's not safe either. If it's too inflated, it would be too hard. And so that would be, that would really hurt you if you hit it and it was overinflated. So we have to make sure it's exactly the right amount. So this is the chemical equation that we have. You should notice right away it's not balanced. So the very, very first thing we should do is balance it before we do anything else. So you can pause for a moment and try to balance it yourself. So I'm going to notice that we have an issue with an odd number of nitrogens over here and an even number over here. So what I'm going to do is I'm going to put a 3 here. Oops. Switch to the right pen. Okay. If I put a 3 here and I put a 2 here, that will force them to have the same number on each side. Now I can notice I have 2 sodiums, so I'm going to put a 2 there. Now it's nice and balanced. So moving on to the rest of the story here. If an airbag is made with 90 grams of NaN3, will it be safe? Assume that 65.1 liters of nitrogen gas are needed to inflate an airbag to the proper size to protect you during an accident. So you should notice that it gives me a balanced equation. I have a starting amount, and I know what I would need for it to be safe. Another thing that tends to happen in these story problems is people get a bit confused because it sounds like you have 2 starting numbers. They say, well, do I start with 90 or 65.1? Well, they're telling you what your answer should be down here. They're telling you that if it's safe, your answer will end up being 65.1. You don't know if that's your answer. You need to start with 90 grams and figure out if it's safe by having this number. If it's too high or too low, not safe, right? So that's one of the things you have to practice is reading the actual story and figuring out which of these numbers is the one to begin with. So we're going to start by making the NaN3 my A value. And then they gave me the density of nitrogen gas. So I'll be able to use density to help me convert back and forth from grams and liters. Okay. So let's start. We're going to rewrite our balanced equation. And then I'm going to label what my starting value is and what my ending value is. I'm starting with A, and I'm ending with B. I'm trying to find out how much gas is made. They gave us grams of A to begin with, and we're trying to get all the way to liters of B on this side. So pause the video for a moment and see if you can write the pathway that takes you from grams of A all the way to liters of B. And don't forget that they did give us the information about density. So you may want to be using that as one of your conversion factors. Okay. So we're going to go grams of A to moles of A. We're going to go from moles of A to moles of B. And then we're going to go moles of B to grams of B. And then we will end with liters of B. Now let's try to label the conversion factors that we would use underneath. I'll do the first one. To go from grams of A to moles of A, you use molar mass. And it will be the molar mass of A. So you can pause and you try to write out the others. Okay, to go from moles to moles, you use mole ratio. And because we're labeling things with A's and B's, it will be the moles of what you want on the top and the moles of what you're trying to get rid of on the bottom. Then you'll go moles to grams will be molar mass of B. And then grams to liters, we'll use that density that they gave us. Okay. If you had a hard time doing that off the top of your head, then you want to just make sure that you're using your mole highway, because that pathway was on the mole highway for you, wasn't it? So now let's start. We start with our known value, which was 90 grams of this one up here. Now I need the molar mass of A. So when I add sodium and 3 nitrogens together, I'm going to get that the molar mass is 65.01 grams per mole. Since I want to get rid of grams, I'm going to put the 65.01 grams of A on the bottom. That's how much 1 mole of A weighs. If I were to stop right now, my grams would cancel and I'd be at moles of A. So now I'm going to go moles of A to moles of B. I'm trying to get rid of moles of A, so I'm going to put the coefficient that's in front of A down here. If I have 2 moles of A, I'm able to make 3 moles of B. My moles of A cancels, so right now I would be at moles of B. Now I'm going to use the molar mass of B. The molar mass of my N2 ends up being 28.02 grams per mole. This time I'm trying to cancel moles, so 1 mole of B goes on the bottom and 28.02 grams of B goes on the top. The moles of B will cancel. I'm almost done. Now I need to use the density, which we have up here, right? So because I'm trying to get rid of the grams, I'm going to put 0.916 grams of B on the bottom, and I'm going to put 1 liter of B on the top. Grams of B will cancel, and I'll be left with liters of B. So if you punch all of that in your calculator, you'll get the final answer. So why don't you pause and see what you get. do it in your own calculator. You got to practice that part also. And you get 63.52 liters. And I don't want to say of B, okay? I want to actually replace it with my formula. That's another thing, right? So it's going to be 63.52 liters of my Try that third time. There we go. Of my nitrogen gas being formed. Now, a lot of people will get to this point, they'll put a box and they'll say, yay, I'm finished, woohoo, I'm all done. Well, you forgot the story part of the question. The story was asking, would 90 grams of our NaN3 make a safe airbag or not? And so we need to compare this to what the safe airbag would be. If you remember, it was a little over 61 liters was safe, right? So this would not be a safe airbag. It would inflate so much, it would be much harder, and it would not be good for you to hit during the accident. Okay. Let's do another one. Example number 2 about rocket fuel. Okay. In 1967, the Saturn V rocket did an unmanned test flight to the moon. It used kerosene fuel to get through the atmosphere into outer space. The kerosene combusts with liquid oxygen on board to form carbon dioxide and water. So kerosene is actually kind of a mixture of hydrocarbons. It's not totally pure, but for the purposes of this problem, we're going to use kind of the biggest, most abundant formula, which you can see here. Okay, pretty big hydrocarbon there. It's telling us that it's reacting with liquid oxygen in a combustion reaction. And sometimes people ask, well, why is it liquid oxygen? Well, it doesn't take up nearly as much space. If you condense it into a liquid, you can get way more on board without needing as big of tanks. Okay, so we're going to need to write a combustion reaction for this. So let's put our hydrocarbon. It's a big one. It's going to react with oxygen gas. Okay, this time actually it's liquid oxygen. Sometimes that messes people up. Don't worry about that. When it combusts, it'll be doable. Okay, carbon dioxide and water because it's combustion. Now, my trick for balancing combustion reactions is I like to, before I even do anything, I like to put a 2 in front of the hydrocarbon right here. That will force everything to be an even number, which will make things a lot easier for our heads. Now I can see that I have 24 carbons, so I'm going to put a 24 over here. Okay, next let's deal with the hydrogens. Well, that's a lot, okay, but I have a 2 over here, so all I need to do is put a 26 in front. Now, let's count up all of our oxygens, okay? Now you have to make sure that you remember that you have oxygens in more than one place, right? So over here, you have 24 times 2, and over here, you have your 26 times just one of them, right? So you add that all together and you end up with a pretty big number, right? 74 oxygens. Well, I can divide that in 2, and I see that I'm going to need a coefficient of 37 over here. Now that, for me, ends up balancing much, much faster by putting a 2 here from the beginning. If you don't, it's not a big deal. You'll end up with the same answer by the time you're finished, but this is typically faster for people. There's a chance if these had all been even numbers that you would have had to reduce at the end, we didn't have to, right? We have a 37 here, so we do not have to reduce anything. Okay. Now that we have a balanced equation, now we can start our stoichiometry problem. So they tell us that we have a whole bunch of kerosene fuel and a whole bunch of liquid oxygen. Would it have enough liquid oxygen to use up all the kerosene in order to get out of the atmosphere? So what I'm going to do is I'm going to make my A value kerosene, and I'm going to figure out how much oxygen that I'm going to need to do that. So I also give you the density here of the kerosene and of the oxygen. Okay. So on the next slide, let's go through it. I'm going to put my balanced equation back up at the top. I'm going to start with the kerosene, and I'm going to try to figure out how much oxygen that would use. Now in theory you could go the opposite way, but this is the way I like to do it. I'm starting with liters of A, liters of kerosene, and I have to try to get all the way to liters of B, which is the oxygen. So I'll do the first one. I'm going to go from liters of A to grams of A. I'm going to use the density of A to do that from the problem. Now you pause the video and you try to do the rest of this pathway and try to label it underneath while you're going. See if you can do that. All right, so grams of A to moles of A, moles of A to moles of B, moles of B to grams of B, grams of B to liters of B. Grams of A to moles of A uses molar mass of A. Moles of A to moles of B uses the mole ratio, which will be B over A. Moles of B to grams of B is molar mass of B. And then grams of B to liters of B, we will use density of B, which they gave you in the problem. So I'm going to actually go through and label what the densities were and label what the molar masses were and things like that before I even start. Sometimes people who have a hard time with the actual dimensional analysis part will have an easier time if you kind of pre-write everything you're going to use up here with your pathway before you even start plugging things into your setup. So the density of A was 749 grams per 1 liter. The molar mass is 170.33 per 1 mole. My mole ratio, if you look up here, 37 over 2. My mole ratio of B, of oxygen, 32 grams of B for every 1 mole of B. And then from the problem, the density of B per 1 liter of B. You're not expected to know densities other than the density of water, For water, the one you should know, kind of the only one you should know, the water density is an easy one to remember. It's 1 gram per 1 milliliter. So that's the only one to kind of memorize randomly. Other than that, everything else will be given to you. So only density to memorize. Okay. So I now have my starting value of kerosene fuel. This is how much they brought on board. And let's see how much oxygen that takes. I'm going to use the density first. I'm trying to get rid of liters of A. So 1 liter of A, 749 grams. Liters of A cancels. Now I need to go from grams to moles using molar mass, and I want to get rid of grams. So 170.33 grams of A, 1 mole of A, grams cancels. Now I need to get from moles of A to moles of B using my mole ratio, which I already know is 37/2. Moles of A cancels. Now I need to get from moles of B to grams of B using molar mass of B. I'm trying to get rid of moles, so I put the 1 mole on the bottom. Almost done. Almost out of room. Now I need to get from grams to liters, so I'll use density. I'm trying to get rid of grams, so I'm going to put the grams on the bottom. 1 liter on the top. Grams of B cancels. Uh-oh. I'm like going off screen over here. Okay, there we go. Liters of B. So, pause the video, you try to punch that in your calculator, see how much of that oxygen you need to burn up all that kerosene. All right, you're going to find out you need a whole bunch of oxygen. It takes a lot of oxygen. Make sure your final answer does not have A's and B's in it. Make sure you put an actual formula. And then the big point of this lesson is make sure you don't forget to answer the actual story part. That is not going to be enough oxygen to burn up all that kerosene. So they did not bring enough oxygen if they wanted to use all of that up. Okay, if you look to see in the story, they only brought 890,650 liters. So they brought but they need this much. So they did not bring enough. Okay. All right. Let's go to the last one. The last one is about hydrogen-powered bicycles. So, we have electric cars and things, but they actually have electric bicycles. So some of these have these rechargeable battery packs and then a little electric motor on them. So you could pedal if you want to, but you could turn the electricity on and have it move the bicycle for you if you want. So the fuel cell has sodium silicide in it. That's kind of how you say it, kind of a funny way of pronouncing it, but we usually say silicide. And so that is what, like the winner of that award used for their bicycles. So let's look at the problem. This time I just balanced it for you. Just kind of got that out of the way. So here's our equation. It's going to react with water. It's going to make that weird compound, the sodium, right over here. Where's my pen? Here we go. So we have the Na2Si2O5, and then in the process, it makes the hydrogen gas. And then that later is what combusts, and that's what's powering the bicycle. So the idea is, instead of having to have canisters of hydrogen gas, which is not super safe, they have this solid material inside a, battery pack, react it with water, make the hydrogen as you need it, burn it as you need it. So you are not riding on top of a bunch of flammable gas, right? So that's the idea there. So it says if you start with 1 kilogram of sodium silicide and your tank on the bicycle can hold 500 milliliters of water, are you going to have enough water to use up all of your sodium silicide? So we're going to use the 1 kilogram as our A value, and they also told us that density of water. Remember, that's the one you need to memorize. Okay, so make sure that you make a note. Memorize that one. It comes up so often, it's so important. Okay, so let's rewrite our balanced equation. Let's label it. Let's write our pathway, label our pathway, do our dimensional analysis, get a final answer, and then make sure we actually answer the story portion as well. So balanced equation. Whoops. 5H2. This is going to be my A value, and I'm looking for this one. I don't know how much water I need. So I'm going to start with kilograms of A. Now you may notice this is a little tricky because we have to get from kilograms of A to grams of A. What we're going to do here is a metric conversion. Sometimes we throw in little bits and extras, right? So this is not on your mole highway, but we should know that we can go from kilograms to grams, okay? So you could do that with King Henry. Moving your decimal before you start, or you can do it with an actual conversion factor that says there's 1,000 grams in 1 kilogram. It doesn't matter which one you want to do. Now we'll go grams of A to moles of A. That will be molar mass of A. Moles of A to moles of B. That will be mole ratio, which is going to be B over A. Then we're going to go moles of B to grams of B, molar mass of B, grams of B to milliliters of B, and we'll use density there. Sometimes people think, wait a second, but we went to liters in the last couple problems. Why are we going to milliliters? Well, that's because the density that they gave you was in milliliters. So density doesn't always have the same units. So you can't just be on autopilot, you have to double check, okay? So the density of water, remember we said was 1 milliliter weighs 1 gram. Okay, molar mass of A was 51.08. Now for our mole ratio, if we look up here, whoops, didn't circle very well. We have 5 moles of B. It'll be over 2 moles of A. My molar mass of B is 18.02 grams of B over 1 mole of B. So now I kind of have everything I need. I'm going to start with 1 kilogram of A because they told me I had 1 kilogram of my fuel or my battery pack, right? I'm going to get rid of kilograms by converting to grams. I'm going to use molar mass of A. I'm going to put the grams on the bottom so that they cancel. 1 mole on the top. Now I need to go from moles of A to moles of B using my mole ratio. Moles of A cancels. Now I need to go from moles of B to grams of B using molar mass of B. I'm trying to get rid of moles this time, so 1 mole will go on the bottom. Grams goes on the top. Now I'm going to go from grams to milliliters using density. So I'm trying to get rid of grams, so that goes on the bottom, and 1 milliliter goes on the top. Whoops. Okay, so pause the video, get an actual answer, find out how much water you would need to use up all of the 1 kilogram that you started with. Find out how much you would need. All right, you would need 881.95 milliliters. Don't put B, put the actual formula of water. Now, sometimes people will say, do I have to use the A and B notation? Could I have just put my formulas everywhere on here instead? Yes, but if you look at that, I mean, look how many times you'd have to write all these formulas. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and then all down here too. It's just a lot. And so like on my answer keys, I'll often just do A's and B's. It's a lot faster, but you don't have to. You could put the formulas if you wanted to. Now we should make sure that we know we're not finished, right? Now we have the story part. So if you remember from the story portion, it told you that your bike holds 500 milliliters of water. But to use up the entire battery, you would need the 881.95 milliliters. Now, that actually kind of makes sense to me that you would run out of water first, because if you were riding your fancy bicycle around and you ran out of your battery pack, it's not like you can just walk into a random store and say, hey, I need another sodium silicide fuel cartridge. Do you have one? Like, people don't have those sitting around in random shops, right? But if you ran out of water, you could fill it up at a drinking fountain or walk into a coffee shop or, the grocery store, go buy a bottle of water. It'd be a lot easier to fill up with extra water if you needed it than to run out of your actual battery pack. So kind of makes sense that they would design it this way to run out of water first. So make sure that you did not forget that story portion of the lesson. Okay, that's the big takeaway here. All right, so that's it, just those 3 problems, walking you through how to do those. It is important that when you are doing your practice that you include certain things. I'm just going to make a quick little bullet point. Make sure you have a balanced equation. Sometimes that's given to you, sometimes it's not. You need to write a pathway. You should always plan what you're doing, right? Label your pathway. You need your dimensional analysis. In this class, we use the line method. I am not going to look at a bunch of messy, random fractions all over your paper. Do it nicely and neatly and use the method that we're teaching you, which is line method. Okay? You should make sure that in that line method you have units. You can either use A and B, or you can use the actual formulas. It doesn't matter to me which you want to use. You should show canceling your units. Okay. You should get a final answer with units, and it should have the formula. That's a big deal. Okay, not A's and B's here, just a formula. Then, because there's going to be so much on your paper, put a box around your answer. Okay. And then make sure, if it's one of these real life ones, that you answer the story question. Also, big part of this. Okay. So when you do your KCQ boxes, not a ton of brand new stuff here, but somewhere you should be talking about what makes these real life ones a little bit different, right? Something to reflect on there. Okay. All right, everybody, that's it for this one. Bye. Hope that was helpful.